is Andre. I guess you can see anything. Oh, this is better. My name is Andre. I'm from Prisma Startup, and I'm actually came from Russia to speak here. Gotta thank the organizer team and Yusuke personally for having me here. And the bad news, kind of bad news, is that I won't be speaking on Swift compiler today. You might be wondering then why you came to the Swift conference and not being speaking on Swift compiler. The thing is that the talk will still involve the compiler. It's just a different one, the Metal one. If you're wondering what Metal is the GPU technology, the kind of OpenGL successor from Apple that they released in 2015. And it comes with the Xcode toolchain for the use. So to better understand what is the motivation of the talk and what we will be covering today, I will first introduce the problem. And I gotta warn you that if you are not a GPU engineer on a daily basis, it probably won't be too relatable to you, but I hope you still understand the idea and kind of the motivation of the tool. So me as a GPU engineer, I have to write a lot of kernels, GPU kernels every day. We work on a computer vision application, so we do a lot of neural nets, computer vision, image processing on device, so we utilize Metal heavily. And the Metal kernels are written into Metal shading language, which is basically a C++ subset with some additional attributes, keywords, and stuff. And each shader has some inputs like textures and buffers. It also has some inputs like metadata of thread position. If you are familiar with GPU programming, you might know what kind of arguments it does have. And the thing is that each kernel, which is written in Metal shaders language, must have a CPU side encoding logic. Usually, you can use like any CPU side language for that, like C, C++, Objective-C, Swift, but in our company we use Swift for the majority of code of our application is Swift, so we use Swift. And those two pieces of codes are very tightly coupled with each other, so they are very connected. So the indices that you use in the kernel, they are usually stated in the C scope. The amount of arguments that you have are also connected. For each shader, you have to create the pipeline states, save it somewhere, so you don't waste the performance on the inference time, right? So you have to move it into initialize. And also, the dispatching logic is usually correlated with the shader itself. Usually, you run shader on the whole texture, so you spend as much threads as the pixels on the texture or maybe other logic. So, those two things have problems. First is manual coherence preserving. So you have to manually preserve that indices in your CPU side code and GPU side code are the same. You gotta preserve that you encode all of the arguments, you create a pipeline state and stuff. And the worst thing about that, you won't get error notifications sometimes even in runtime because Metal still work even if you mismatch the arguments and stuff because it's on too low level. It will just work even on an empty texture or empty buffer and stuff. So that's introduced a lot of problems when you change the shader, forgot to change the CPU side code, and then you have to spend multiple hours trying to debug code which is just wasn't coherent. I was looking for a solution for a long time for this, and the first one was to use reflection. In Swift, it has mirror that can reflect the CPU types, but we can't use that for GPU types, so Metal introduces their own reflection. It's called MTL reflection, and while they create a pipeline state, you can get the metadata from the shader. Metadata contains some useful information on arguments like indices, the argument names, the texture types that you use, access level, precision, and blah, blah, blah. So it has basically everything that you need. But the thing is that those information is only available at runtime. To kind of better utilize that, I use the Swift dynamic member lookup feature, which basically allows you to kind of use the properties as a string literals. That translates the code from a.foo to a dynamic member foo. to kind of build the dictionaries where the key is the name of the argument and the value is the mem buffer or texture, and then just use it as a class that you initialize with a function name, and then you just assign arguments in Encode. But it still had problems because those properties are not like statically checked. They're basically string literals in the form of property. You still have to preserve that those properties are written correctly. Plus, you have to use the name of the shader that is correct. So if you rename the shader in the GPU code, you have to rename it here. And the GPU dispatching logic is still not encapsulated. So the user is responsible to manage it yourself. So the compute command approach that I tried first wasn't enough. So I stick to the encoder pattern. Encoder pattern is somewhat I invented for myself, but it is of course inspired by metal performance shaders. It's just a way to organize the shader code, right? So this is usually a class that stores a reference to a pipeline state to cache it and reuse it. It usually has an initializer, which has always has a library argument that you can create your pipeline state from. And it usually looks like this. So you just assign the pipeline state from library with a particular name. And the second thing the encoder has is encode method. And this method just takes all of the arguments that the shader takes and just encodes it into the GPU pipeline. So basically it encapsulates the GPU logic, GPU encoding. And the usage is pretty simple. So you first in initializer state, you just create the encoder and then you use it. So this approach has obvious benefits. You have a nice code organization, so everything that is related to a particular shader is encapsulated and stored in a separate file. You have static argument info because you have a method which is statically typed where you can state the arguments that you use, and everything is, the logic of dispatching is encapsulated as well. But the cons here is that you still hardcode indices inside the static method that you have. You still hardcode the function name inside the initializer. And those encoders are very similar to each other with only like slight difference between each. So it just didn't feel good. And so I looked at the situation and it was that the generally encoders and me was well paired, so we just it made our code base better. But on the other hand, writing those encoders was really not the best experience that you had because there's a lot of boilerplate code which you have still manually preserved coherence between two languages. And I thought, well, what's the particular things that are connected between the encoders and the shader? So the first is, of course, the name. So you usually name the encoder after the shader. So if your shader is called process, you call your encoder like process encoder. Also, the encode method arguments are tightly coupled with the arguments that you have in the shader. So if you have two texture arguments in your shader, you will have those into method of encoder. And the encapsulated logic also is tightly connected. So if you use textures, you probably want as my threads as a texture, so you kind of use it inside. So the question was, can we code generate them? Because it would kind of eliminate all of the problems and also reduce the amount of code that we should support. And the code generation approach is already popular in Swift community. We have Sorcery, very popular tool to generate code. Plus, we have a lot of smaller tools like SwiftGen, RSwift, Natalie, and so on. And the Swift compiler team has its own tool for generating boilerplate code. It's called swiftckaigi, which stands for generate your boilerplate. So the code generation approach seems to be like proven to be good for code bases. So we try to dig into it. It should be doable since other libraries and other stuff do. But how do we parse metal shaders? To understand what approaches you have for parsing the language files, we first looked what we had for Swift. Swift has the thing called SourceKit, which is basically responsible for parsing all of the Swift-related stuff. It can usually used by IDEs for indexing, syntax coloring, and stuff like that. And there is a small infrastructure around the source kit, like the source kitchen library, that allows you to have a runtime access to source kit Swift link that uses the IB analyzer and stuff. There is another tool called Swift Format by Encode that introduces their own tokenizer and lexer, but that seems to be too complex for our tasks. Another thing is the library called NTLR, but the problem with this library is that it's so complex, it has dedicated books on how to use it, so that maybe that's not what fit for the situation that I have. So I started to look in other ways of parsing metal shaders by leveraging existing tools. And for that, we first have to see what we know about metal shaders. Metal shaders are known to be shipped inside an Xcode, so it comes with the Xcode ship. The compiler is proprietary, so unlike the Swift compiler, it's not open source, it's closed source. Metal shader language is superset of C++ subset. So basically it's C++ with some features added and some features removed. And we also know that Apple loves the LLVM and Clang thing and invests a lot into that direction. So the hypothesis was, if the metal shading language compiler is a Clang fork. First I compared the helps, and they looked pretty familiar, so maybe this is just the right direction. Next I compiled the shaders into a standalone library and checked the header with the file tool and saw that this is LLVM bitcode. And if you look on the header more closely, we can see a magic number, which is the so-called LLVM bitcode magic number that states that this file is the LLVM bitcode. So it should be kind of confirmation that Metal compiler is based on Clang because it has a very similar functionality with Clang tool, and also the produced files are LLVM bitcode files. So the plan was to use libclang which is the library to work with compiler as a library in runtime from your tools, which basically provides the C interface. It can do a lot of bunch of things like parse the AST, tokenize your code, lex your code, index your code, position your cursor, and stuff like that. So, but the most interesting part is that libclang can build and read AST dumps from the Clang compiler. What is AST is basically known from the previous talk. You probably know, but just to quickly recap, AST is abstract syntax tree that represents your code as a tree of operations that just a better abstraction representation. I use the awesome Clang Swift wrapper library just to have a more pretty Swiftier API. And the plan was to dump AST from the Metal compiler, load it as a regular C++ AST into libclang, hope that everything will go okay, traverse and extract the shader signatures from the AST, and that's it. So the first step when successful, I just added emit AST flag to the command. Next I load the AST as a translation unit to the library, but it's thrown an error, the fatal error. So the regular libclang cannot read customized ASTs by Metal. I tried different approaches, like maybe tokenize the metal shaders by libclang with other functionalities, but it didn't really work well. So what I tried to do is I used the xclang directive that is usually used to pass additional arguments from your tool to linker if used by xlinker, or you can use xclang to pass proxy calls to xclang to execute additional comments. And additional comments that I tried to use is AST dump from the regular clang. And what I saw is actually the human readable AST dump from metal shaders with a slight error in the downstairs, but that was okay. The whole AST is just among our eyes. And the thing is that this is a very structured AST actually. So if you look precisely, so it starts with a padding that represents the current level of the tree. Next it comes the name of the node that represents. Next we have the unique identifier of the node. The source location, it can be a line, a column, it usually contains a file and stuff, and the rest is just depends on the type of the node. So it can be an operator, a type, or a value, depending on what nodes you require. So this is definitely parsable AST dump that we can parse and kind of reconstruct the AST from the ground up. That's exactly what I did. To eliminate the problem with the error, for some reason, Metal Compiler wasn't happy with that me was trying to dump AST, so it was emitting a strange error. To eliminate that, I just used the -e flag to say only run the preprocessor and do not compile my shaders. That was enough for that. One more thing that I was fighting with is that the AST dump was syntax colored. So it was filled with ASCYY special symbols to colorize the code, but the Clang has additional very handy flag no color diagnostics that will kind of help to preserve it. And after I wrote this very simple parser, I was able to reconstruct the AST of the metal shaders as a internal representation in my code. And the last thing was that I had to find kernels inside those ASTs, and then just to extract the argument info to kind of use the generation. So I first looked manually by eyes, what if there are pattern of how arguments are represented in the ASTs, and found out that that kernels in metal shaders are regular function declarations, but inside of their ancestors, or like the child of the tree node, they have a node called metal kernel attachment without any parameters or subsequence challenge. So basically, the task was to find all nodes that has the type of function declaration. And among their children, they have metal kernel attribute. Because not every function declaration can be shader. You can have general purpose shaders or general purpose functions. You can also have general purpose fragment shaders or vertex shaders. So you have to kind of extract only the kernel shaders that you want. And this is how I created a tool called MTL Swift. What it does is essentially kind of the following. So it calls Metal Compiler to dump the AST. It parses it internally into internal representation. Then it triggers the AST by regular recursive search and extracts the kernel shaders into a separate abstraction that I have. And then I wrote a very simple Swift generation code that just generates all the encoders for each shaders with additional stuff. Moreover, I was able to not only analyze the arguments of the shader, but I also was able to see inside the tree whether or not the shader uses, for example, the function constants. Function constants is just like compile time constant from metal language. So if the shader appears to be using them, I smartly generate the initializer that accepts the compilation values. So you have a fully fledged generated Swift code from your shaders right away. One thing I added more is that I wanted to have more control on how my encoders are generated. So I added the custom annotations that sit inside the docstring, which is basically also parsed by AST and provided to you by AST node called docstring. And I use the Swift link convention because I think this is just fine, so semicolon just split the declaration. And among the annotations that I introduced were, you can modify the Swift name of the encoder, you can introduce a custom name, you can introduce a custom access level, you can make it public or private, you can introduce new custom Swift parameter names, more Swiftier if you use underscore syntax in metal, it would probably not be very handy in Swift. Plus you can have Swift parameter types, and most importantly, you can customize the dispatch. You can either say dispatch the constant amount of threads, or please dispatch the amount of threads that is equal to the size of the texture and stuff like that. And as a result, my code base, which was really hard, if you ever wrote GPU code base, it's very expressive, and so there is a lot of code. So most of the code is also usually dedicated to encoding the shaders, and it was just removed because we don't have to kind of manually support that code anymore. We can just regenerate it. So as a result, we got a tool that removed all of the nasty debugging problem, because we don't have to preserve manually the indices between the CPU side and GPU side. We have less code to support, drastically less code to support, and drastically less code to write, because even though the encoders are easy to write, it's boring, it's boilerplate code, nobody wants to write boilerplate code basically. So the usage is that we distributed the tool in multiple ways, but usually we incorporate it as a build phase of the application. So the first step of the compilation is to grab the shaders, generate the encoders, feed it to compiler, and then proceed to regular compilation of the application. And the usage is pretty much simple. So we have just a tool where you can say mtl watch is a special command that will observe the changes to your files of the shader, and once you hit the command S, so once the file is modified, it will smartly regenerate all of the encoders, so the process is very smooth. Or if you want it to happen only one time, just to force the generation, you just say mtl generate, and it supports like additional stuff like recursive search, multiple outputs. It can watch not for individual files but a folder, so it's pretty convenient. So if you use the Metal, you should definitely try, because our code base became much better after we introduced it. So that's it for today. Thanks for having me once again. This talk wasn't about the Swift compiler, but I hope that the idea of using the AST dumps for generating other code can be like inspirational or motivational to you. If you have some question, I'm ready to answer them right now. The link to the mtl Swift is provided on the slide, and you also can reach me throughout the social media. Thank you.
別に英語で聞いてもらってもいいし、日本語で僕はトランスレーション、僕以外にイングリッシュスピーカーいるし、翻訳してもいいんで、どっちでもいいです。
はい、翻訳してもらっていいですか。すごい合理的でいいアイデアだと思いました。で、メタルコマンドのオプションの -x クランはどうやって見つけたんですか。
So he said, thanks for your talk. How did you find the dash option for the method?
Well, this is just actually the same notation is used in Swift Package Manager. So in Swift Package Manager, you can use -x linker to pass stuff to linker, -x compiler to pass to a compiler. So I've just tried, maybe Apple has the same notation in the middle, and yes, it did.
It's fun.
Any questions?
AST をパースするアプローチってなんか微妙にSwiftコンパイラーでも同じように、ダンプ AST の結果をパースするっていう戦略がアイデアがあるんだけど、なんかカッコの対応とかインデンツとかおかしかったりして難しいんだけど、メタルの裏のクランが出す AST ダンプってパースしづらい変な部分あったりしないのかな。
So his question is dump AST possible? Because like the one from Swift compiler is not actually possible. It's quite difficult first because it has like many brackets, parents, etc. So is it the first possible? If it is, if it's not, did you have any difficult time to dump AST?
Actually, the human readable ASTs are very parsable. So especially given that, well, this is even though this is like a Metal compiler AST dump, actually this is just a C++ AST dump, which is much more complex than Swift, from my opinion. And given that the AST from C++ is parsable, I'm sure that Swift AST is parsable as well. I never tried it myself, but it wasn't too hard. The parser that I wrote was super dumb. Like it was a bunch of ifs, like if the node name equals something, then else. So just very dumb parser. But I wrote it in maybe 2 days, so that should be totally possible. I think everybody wants to go to lunch already. Yeah.
Thank you very much.
Yeah, thank you.